For environmental engineering, we deal a lot with environmental measurement, which is an act of data collection related to assessing environmental systems in terms of its physical, chemical, and biological factors that affect human and environmental health. We need a language to express these environmental measurements, and this is basically expressed through chemical concentration and its units. Concentration refers to the amount of a substance in a particular quantity of space, or simply it is the ratio of solute in a given solvent or total solution. Herein, we mostly refer to chemical concentration of substances. It is one of the most important concepts in relation to freight and transport of chemicals and their treatment in both natural and engineered systems. Basically, knowing the concentration of something such as pollutants in the environment, may it be in air, water, or soil, will help us understand how the chemicals or pollutants are moving within the system or between different media. Concentration also helps in determining the rate of many chemical reactions, as well as knowing its level of safety or toxicity. For example, atmospheric particulate matters such as PM2.5 or particulate matters that have 2.5 microns in diameter are often included in air quality reports. As these are extremely fine particles, they stay longer in air and have higher tendency for humans to inhale and can potentially penetrate the lungs and cause diseases. Particulate matters in air are reported in units of microgram per cubic meter. PM2.5 concentration greater than 35.4 micrograms per cubic meter is considered unhealthy. Another example is concentration of contaminants in water such as arsenic. The inorganic form of arsenic poses a serious risk to human health. Thus, its concentration in drinking water must be controlled. According to the Australian Drinking Water Guidelines, safe level of arsenic in drinking water must not exceed a concentration of 0.007 milligrams per liter. In environmental processes, we deal with concentrations all the time to calculate the mass of contaminants in various media. Concentrations are expressed in different units depending on the kind of chemical and where it is located, such as in air, water, soil, and sediments. Hence, it is important to familiarize with the different concentration units and their conversions. There are several ways to express the concentration of a solution. The amount of solute and the amount of solvent will determine whether the solution is concentrated or diluted. A concentrated solution has more solute dissolved in a given solvent, while a dilute solution has lesser dissolved solute. We can take for example when making a cup of coffee. We take 1 tablespoon or approximately 5 grams of coffee powder and dissolve in 300 milliliters of hot water. We can then choose to add or not add a teaspoon of sugar to make the perfect coffee drink with taste to our liking. However, if we take the same 1 tablespoon of coffee powder and dissolve it in a flowing river with thousands of liters in volume, the taste would definitely change. This is directly related to changes in concentration, which has environmental significance as well. Concentrations can be represented based on mass units, including mass of solute per total mass of solution, or mass of solute per total volume of solution. If we are referring to concentrations in soil, we usually use milligrams per kilogram as the unit. For concentrations in water or liquid, we normally use milligrams per liter, or parts per million, or ppm. Take note that in most dilute aqueous systems, especially with water as the solvent, 1 milligram per liter is equal to 1 ppm by mass. This is considering that water density is equal to 1,000 grams per liter. We can approximate many wastewaters and natural waters as dilute solutions. For air units, we usually use 2 forms: the microgram per cubic meter or the parts per million by volume, or ppmv. The microgram per cubic meter is usually used for particle concentration in air, or as commonly called particulate matters or PM, or also used for solid contaminants in air such as lead. For checking the total suspended particulate or TS free from air, a known volume of air sample is passed through a filter, and the change in weight of the filter signifies the accumulation of particles on the filter. And if we divide this one with the total volume of air that passed the filter, we get the microgram per cubic meter concentration. The units of ppm by volume or ppmv is usually used for gas concentrations, especially if the pollutant exists as gases. For example, 100 parts per billion of sulfur dioxide in air. ppm by volume is a usual representation for air concentrations when the contaminant is a gas, because when the volume of air expands, the volume of contaminant in air also increases together. Thus, the contaminant concentration remains the same. But if the contaminant is a solid like particulate matter, if the volume of air expands, the amount of solid contaminant remains the same. Thus, the concentration changes. It is also useful to use the volume ratio unit when converting from units of volume and moles in accordance with the universal gas law, which is PV equals nRT, in which case the volume fraction is equal to the mole fraction. When working with chemical reactions using aqueous solutions, use molarity as the concentration unit. Molarity is the number of moles of compound per liter of solution. In many cases, chemical concentration found in environmental systems can be quite small, so that the units of millimolar or micromolar are used. The M unit or the molar unit here can be read as molar. Molarity can be converted to milligrams per liter by knowing the molecular weight of the compound. The molarity in moles per liter is multiplied to the molecular weight in grams per mole, then multiplied by the conversion factor of 1000 milligrams per gram to get the milligram per liter equivalent. There are also some special ways to represent some concentrations, especially when involving various compounds of the same species, to include the contributions of different compounds, such as those formed by nitrogen and phosphorus, water alkalinity and hardness, and even greenhouse gases. The concentration can be expressed as a common constituent. Let us take, for example, phosphorus. Considering a wastewater treatment plant where we want to know the concentration of total phosphorus in the wastewater, it can exist in the form of inorganic forms such as orthophosphates, polyphosphates, metaphosphates, or as organic phosphates, but all of these actually contain phosphorus. Instead of referring to them individually, we can represent the total phosphorus which exists in many forms as one unit, and present it as milligram phosphorus per liter or milligram per liter phosphorus. What we need to do is to convert all individual forms of phosphorus into milligrams per liter phosphorus by knowing the molecular weight of each individual species, the molecular weight of phosphorus, and a simple stoichiometry. In the same way, we can do this to nitrogen, which can exist as ammonia or NH3, nitrate or nitrite forms. We present it as total nitrogen in the unit of milligrams nitrogen per liter or milligram per liter nitrogen. The alkalinity and hardness of water are also contributed by different species. For example, hardness is mainly due to divalent ions, particularly calcium and magnesium, which are the most abundant divalent ions in natural waters. So instead of knowing the contribution of each divalent ion to hardness, we refer to their total contribution in units of milligram per liter as calcium carbonate. We can calculate this equivalent value by knowing the concentration of individual divalent ion, then knowing the equivalent weights of calcium carbonate and the divalent ion species. In the same way, alkalinity is a measure of multiple species in solution, such as those bicarbonate, hydroxyl, and others. In this case, it is also represented as milligram per liter as calcium carbonate. Another example is the effect of various greenhouse gases to climate change. Each identified greenhouse gas differs in its ability to absorb heat in the atmosphere, which translates to each to its global warming potential, or GWP. The GWP is a multiplier that is used to compare the emissions of various greenhouse gases to a common constituent, represented as carbon dioxide equivalents, meaning the amount of carbon dioxide that would have the same global warming potential when measured over a specified time scale, usually 100 years. For example, 1 ton of methane emissions equates to 25 tons of carbon dioxide emissions. In this video, we have discussed about the importance of knowing the chemical concentration to aid in assessing an environmental system or problem. We learned that concentration is the driving force behind many environmental processes, and that there are different ways concentration is expressed. We also learned that units of concentration vary depending on where the contaminant or the species is located, may it be in air, water, or soil. The concept of concentration is very important in order to proceed in analyzing the various processes happening in the environment, from just simple measurements, use and mass and energy balances, and for treatment and management of contaminants. Refer to sample calculation videos for exercises in use of concentrations.